Hello everyone, and welcome to this four-part mini-series on Archimedes and the mathematical contributions he made. In this part, we'll be talking about the quadrature of the parabola, which is one of the works that he produced during his life. And so to start off, I wanted to start off with how he started it off. He says, I set myself to the task of communicating to you, as I had intended to send to Conan, a certain geometrical theorem which had not been investigated before, but has now been investigated by me, and which I first discovered by means of mechanics and then exhibited by means of geometry. I am not aware that any one of my predecessors has attempted to square the segment bounded by a straight line and a section of a right-angled cone, or a parabola, of which problem I have now discovered the solution. For it is here shown that every segment bounded by a straight line and a section of a right-angled cone is 4/3 of the triangle which has the same base and equal height with the segment. And so that can be kind of hard to wrap your mind around, right? Trying to visualize what he's talking about. But hopefully as you watch this video, you'll be able to kind of understand a little bit of what he's going at and kind of how he gets there. So with the first proposition, he says, if from a point on a parabola a straight line be drawn, which is either itself the axis or parallel to the axis as PV, and if Q prime be a chord parallel to the tangent, so there's PV, and if Q prime be a chord parallel to the tangent, so there's the there's the tangent, and there's Q prime, right? You can see that they're parallel. At P and meeting PV, then QV equals VQ prime. So we know that he's saying that this distance here and this distance here are the same. And then he also says, controversially, if QV equals VVQ, so if you start off with the segment here, the lines here, and you split it in half and you bring it straight down, you can know that it is parallel to this line here. In proposition 2, Archimedes says, if in a parabola Q prime be a chord parallel to the tangent at P, and if a straight line be drawn through P, which is either itself the axis or parallel to the axis, right, it's the same setup as last time, and which meets Q prime in V, and then the tangent at Q to the parabola in T, then PV equals PT. So, right, same thing as last time, but if you take the line that's tangent at Q, you draw it down and you connect it to this line here, Archimedes is saying that this distance is the same as this distance here. Okay, so then he spends the next several propositions discussing how he came about this through mechanics, right? He talked about that in the introduction there. And so this is a little bit out of the scope of this video, and so I'm not going to include it, but here are a couple of interesting diagrams that he has in there, and kind of it shows you just how kind of crazy and how much he thought about this in order to try and prove it. Picking up in proposition 19, he says, if QQ be a chord of a parabola bisected in V by the diameter PV, and if RM be a diameter bisecting QV in M, right, so if we split it in half, we have M there, and then we draw another line straight down, and RW be the ordinates from R to PV, right, so we've got that line there, then PV equals 4/3 of RM. So he's saying that this distance here is 4/3 the distance here. And you can see here kind of how he proves that. You're welcome to try and work it out for yourself using, all that you know about parallel lines and parallelograms and all of that. It's kind of a fascinating little exercise. But he ultimately, he ends up proving that in this proposition. In proposition 20, he says, if QQ be the base and P the vertex of a parabolic segment, then the triangle PQQ is greater than half the segment of PQQ. So if we draw a triangle here, he's saying that this area here is greater than half of the area of the total segment. And then he says corollary, it follows that it is possible to inscribe in the segment of a polygon such that the segments left over are together less than any assigned area. So that basically means you can keep making little triangles right in here, and then a triangle in here. And as you do so, you'll never exceed the size of the segment here. And he ultimately proves all of this using parallel lines, right? We know that this area here, the triangle area, is half the area of the parallelogram, but we can see that the parallelogram, the area of the parabola is greater than half of the area of the parallelogram. Moving on to proposition 21, he says, if QQ be the base and P the vertex of any parabolic segment, and if R be the vertex of the segment cut off by PQ, then the area of PQQ equals 8 times the area of PRQ, right? So like I was saying, if you draw these little triangles in here, he's seeing that the area of this here is 8 times the area of this here. And this becomes very important later on, and he ultimately proves that, again, using kind of the parallelograms. If you want a very fun exercise, try proving this yourself. It's a very fascinating kind of way of thinking about it all. Moving on to proposition 22, he says, if there be a series of areas A, B, G, D, each of which is 4 times the next in order, and if the largest A be equal to the triangle PQ inscribed in a parabolic segment, and having the same base with it and equal height, then the sum of all of the areas will be less than the area of the segment. Right, so he's saying if you take this and you make triangles, and then you make more triangles, and you just keep making triangles, no matter how many you make, you will ultimately be less than the area of the segment. Which just kind of makes sense, right? You'll never be leaving the segment with your lines. Proposition 23, he says, given a series of areas, A, B, G, D through Z, all of which A is greatest and each is equal to 4 times the next in order, then A plus B plus C, and so on and so forth, plus 1/3 of Z equals this. Again, it's a little bit complicated, kind of hard to think about, but basically he defines that if you sum up a series of areas following this pattern, then you ultimately end up with the 4/3 of A, of the greatest area in there. I mean, this is very similar to this specific identity here, and that's likely where Archimedes got this idea. Moving on to proposition 24, he says, every segment bounded by a parabola and a chord QQ is equal to 4/3 of the triangle, which has the same base as the segment of the equal height. Right, so this is the last proposition. This is his answer. He says, suppose K equals 4/3 of the area of PQQ. He then asks a couple of questions, right, trying to prove that. He says, well, suppose that the area of the segment is greater than K, right? Let's see if that works. He ends up disproving that using proposition 23. The math is a little bit more involved, and we don't have time to talk about that, but he ultimately does prove that. Then he says, suppose, if possible, that the area of the segment is less than K. And he ultimately disproves that using proposition 22. And then he says this. He says, thus, since the segment is neither greater nor less than K, that means that the area of the segment, which equals K, equals 4/3 of the area of PQQ. And so that's ultimately the conclusion that he comes to, right? That's what he said he set out to do in the beginning. And it's very fascinating that he's able to figure that out and come to that conclusion. And, this is a very fascinating way of looking at it. Well, now we have to ask ourselves, how can we do this today? One of the major mathematical things, mathematical concepts that's come since then is calculus. And with that, that gives us the ability to find the area under a function. Ultimately, who contributed to this idea? Well, there were several key contributors, including Kepler, Fermat, Roberval, and Cavalieri. They all did work in trying to find the area of shapes using increasingly smaller rectangles. not too far distant from what Archimedes was doing with increasingly smaller triangles. Newton and Leibniz, in particular, came up with the fundamental theorem of calculus, which is very important and is what we'll use to ultimately prove what Archimedes did. And so what is the fundamental theorem of calculus? Well, for those of you who haven't ever taken a calculus class, it basically says that you can find the area under a segment if you have, say, like from A to B here, by taking the integral of the equation and subtracting the integral at B minus the integral at A. That's kind of what this is saying. And so how is this useful? Well, we can use that to find the area underneath these specific equations, right? So here we define the equation of our parabola. I'm going to do ax squared. I use a because that's kind of the scaling factor, and just to show that this is applicable to all parabolas. And you can see here, as we kind of do the math, right, we find the integral at each place, plug it in, and we ultimately come up with this final equation here. We can do a similar thing with the area under the segment. The math is just a little bit more messy, but we ultimately come up with this area here. And so ultimately, what is the area of the parabolic segment, right, in both of those? Well, we know that that'll be the area of the segment, and then you can subtract the area of the parabola. And doing so gives you this kind of messy equation, but it'll all make sense later, and it'll cancel itself out, and it'll look great in the end. So now let's try finding the area of the triangle. I did this using the shoelace formula, and ultimately you can, when you plug it all in and you kind of simplify it all up, you get this equation here. Again, a little bit messy, but it'll all cancel out in the end, I promise. So let's try and find the ratio of the area. So I defined the ratio as this capital R here, and so I just found, set up my equation here, multiplied by the reciprocal, multiplied it through, factored a little bit, and then you can see here that these are going to start to cancel out all the way along here, leaving us with 8 over 6, which simplifies to 4 over 3, just like Archimedes said. And this is honestly, I thought this was so fascinating because the way that he did this was using progressively smaller triangles, and the way that we do it is using progressively smaller rectangles. And we use the same ultimate principle, but nowadays we can use a little bit more of a general formula for solving this for any different kind of equation. But I thought that was so fascinating, and I hope that you learned something in this video. I hope you enjoyed it. Again, feel free to check the link for the descriptions and a little bit more of how to do this, and some resources and learning a little bit more about this stuff. But I hope to see you in the next video, and I will see you later.